You have questions on the decision trees so far? Everything is okay? Okay, so if there are no questions, let me just continue. So now, just to recap a little bit, so we are estimating a function given certain input parameters. Okay, in this case, Boolean functions of input parameters A, B, and C. And then we create a decision tree that will define the relationship that is determined by the Boolean equation. And we write down all the possible relationships in the input parameters to come out with a Boolean decision. So those relationships are shown in the table, and then we check those decisions based on the table according to the decision tree that was created. So we have given two possible decision trees that will be the model that can be used in that given Boolean equation. Okay, so what we are saying here is depending on how you choose your nodes, A, B, and C, that is your nodes consist of your parameters, okay, input parameters or properties, or whatever name you call them, okay. So that this consists of all the variables that are used in the choice of the parameter. Then you will be able to come out with your own choice of a decision tree, of the structure of the decision tree. So now we are saying that it is dependent on your choice of node. So in this next slides, in next set of discussions, I will discuss on how we are going to choose those nodes. What in the normal practice in the decision tree computation, what is used in order for us to choose which node will come in first, and which node will come in second, and which node will come in third, and so on. Okay, so that we can come out with a more efficient decision tree. Okay, so let me share my screen. Okay, I assume you see that. So now, so this was the tree that we discussed, and the next we are given another example, a table of data. This is what we mentioned before at the start of the class about the miles per gallon or kilometer or liters per kilometer in the metric measurements. So this normally computed by people who would want to save money. Most people would want to save money in their transportation. Okay, so they want to choose a certain model, certain characteristics in terms of cylinders, displacement, horsepower, and so on and so forth, and then come out with a decision whether the miles per gallon of that particular choice of all these input parameters will give you a good chances or a good position of saving money. So if the miles per gallon is good, then you can save some money. If it's bad, maybe you wasted a lot of money in that particular choice of car that you made. Okay, so again, they're given here, for example, 40 data points. That means there are 40 of them, 40 data points based on how many input parameters here. 1, 2, 3, 4, 5, 6, 7 input parameters. Okay, and in this case, this is a column of the output of parameter Y consisting of good, bad, good and bad only. Okay, and then this is the function f of x. So given the input x, which is this, given the input x, which is all these parameters, that's the input. We want to know the function f, which is the decision tree that will give us the output y. Okay, so I hope it is clear. So again, then let's move to create that decision tree. So how do we create this decision tree? Okay, so we need to know which one we should go first, which parameters should go in first as the first node, whether cylinders, maker, or horsepower goes here or maker goes there. Okay, so each internal node tests an attribute. We call it a parameter, but an attribute in this case, cylinders, maker, and horsepower. So each branch, okay, each branch assigns an attribute value, xi is equal to b. Each leaf assigns a class y of good, bad, good or bad, in this case. To classify the input x, transverse the tree from the root of the leaf and output the label y. Okay, so here transverse to make the input x, whatever value that is assigned to the input x, whether cylinder number 4, for example, if its number of cylinder is 3, it's good. There's no need to decide whether it's not anywhere dependent on the maker or the horsepower. The number of cylinder is 3 only, then you have a good miles per hour, or miles per hour of coverage. Okay, why? Why? Why do you think so? We are mechanical engineering. You should know this. Why? The least number of cylinders, the miles per gallon, is the best. You don't need even to think what maker and what horsepower is your car. Mupati?
Because it's not so much.
It's very bad. The sound is very bad. Okay, let's call someone else. Mupati, your sound is very bad.
A few cylinders, then it means it doesn't have the capacity to.
Okay, sorry, I have to call someone else because your sound is very
bad.
Okay, let's call someone from the dorm. Mr. Haburone. Haburone, can you answer?
Okay, I'll look into it.
Okay, sorry, we have to call someone else because your sound is not good. Haburone. We cannot hear you. You don't have any idea? Say something.
Yes, I have no idea.
We're from mechanical engineering. We don't know when the number of cylinders is small. Number 3 cylinders. What does it mean when you only have 3 cylinders in your engine? Okay. Sepo, Olefa. Number of cylinders meaning what? You have no idea. Then you graduate from mechanical engineering department and your uncle will say, hey, can you fix my car? You already now a graduate from mechanical engineering. You should know how to fix a car. And what you do? Huh? No, we don't discuss that one in class. Oh, really? They don't discuss that one in class now, nowadays. Huh? It's very, you spend 5 years in views and you don't even know how to fix my car. Okay? I won't help you find your Libola, like that. Huh? You get married here by your uncle, right? Your uncle is the one making arrangements for you. That's what I heard. Right. Why it's always good. Moses, okay. Moses Mulatli.
I have a problem with my video. It's refusing to start up.
Okay.
I think cylinders are they're like chambers where the gasoline is being burned. So
Yes.
the more the number of chambers that you have, it means you're gonna burn a lot of fuel in a short amount of time.
Yes.
So I think that's the answer.
Yes, that's correct. Okay. So that means that lesser chambers to burn, lesser fuel to burn, to run a certain distance. Yeah. So why don't we have just few cylinders there if that's the case? Why do we need to make more cylinders?
I think that is the issue of wanting to, because with more cylinders, it means you can generate higher horsepower. So the takeoff of the vehicle is going to be way higher. So mostly they do it for sports utility vehicles and those fast cars.
Yes, exactly. Yeah. So Moses is the only one true-blooded mechanical engineer. Is that the case? So when you need more power, of course, you need you would need to burn more fuel. Okay. But if you really need to save gas and not worry about power, maybe you only 3 cylinders is good for you, especially if you're driving in a flat surface. There's no going up and down. But if you only have 3 cylinders, well, and you have many people in the car, it's possible that it cannot, it cannot go go up the hill, and then you need to ask your friends to go down so that you can, go up the hill. Okay. But for sure, it burns less fuel for a given distance. So of course, it's always good, it's fuel saving, vehicle. Okay. But is that what you want? Then that's another case. I want more cylinders because I want more power. Okay. If you want more power, then we need to know what are the other parameters, whether it's a good or bad in terms of miles per gallon. Okay. So now that is the thing that we are looking at here. Okay, so learning decision trees is hard. Okay, learning the simplest or smallest decision tree is an NP complete problem. Okay, non-polynomial complete problem, non-deterministic polynomial problem. It means that each solution can be guessed or verified in polynomial time. Okay, and then it can be solved by a restricted class of brute force search algorithm. Okay, that is the NP problem. If it is not NP complete, non-deterministic means that no particular rule is followed in the guess. Okay, so non-deterministic, no particular rule. It could be any rules that will apply to it. Non-deterministic polynomial, NP problem. So if it's NP complete problem, so that means that it follows the rule that it can be guessed. There's no particular rule that can be followed in terms of to make the guess to find the solution for that problem. Okay, that is the NP problem. Okay, for NP complete, what is the difference between NP problem and NP complete problem? Okay, well, it's completely NP. Okay, well, is there an NP that is not complete? Yes, there's NP that is not complete. It's NP that is an NP incomplete problem. Okay, but anyway, okay, we're just saying here that there's no deterministic time. It can be your solution can have no particular rule to follow. Okay, so it can be, but then it can be solved. It should be solved. Let me verify this information. That NP complete problem, it can be solved in a polynomial time. Okay, solution can be guessed and verified in a polynomial time. Okay, anyway, let's not dwell too much on this one. Then we can resort to greedy heuristics. That means you start with an empty decision tree and split on the best attribute or feature, or you can come out with some recourse on how to solve the problem. So before we go to the uncontrolled sense, that means that we don't really know what will go on and how much time we need to know to find the solution. Then let's start with something, some decision, some way to decide on which node or which way we should go before all these parameters are given to us, before we build that particular tree. So which one, for example, in this case, if you are given a table here, X1 and X2 inputs, and your output is Y, okay? This is about a coin flip data. And so we say that if your input X is true, then input X is true, then there are 4 cases of true and 0 cases of false. So that's the case here, the output. So we are looking at all the possibilities of true and false. So 4 here, 4 true and 0 false. If it is false, if X is false, then you have 1 true and 3 false. Okay. If your input is X2, I mean, this is just the data. We're just saying this one. So this is the data that is table that given to us. And so the output is that if you have X2 being true, then the output is true. There are 3 possibilities of the output to be true and 1 possibility of false. And then here, if the X2 is false, then half possibilities. So we use counts of leaves to define probability distribution, so we can measure uncertainty. Okay, so now how do we measure this uncertainty? So we measure uncertainty. Good split is that if you are certain about a classification after the split, that is what we are going to do. So after we split, there will be more things, will be more deterministic. Deterministic, that means that we will be more and more comfortable. We are more and more sure about our decision. Okay. So the problem that we will be looking at here is the probability of certain things being true, probability of highly being true, or probability of highly being false. Okay. Or probability of half true and half false. Okay. I mean, half true and half false. So how do we go about those probabilities? Okay, so here, for example, there can be given Y, okay, the probability being A, and then these are all the probabilities, or you have input A, B, and C, A, B, C, and D. This is all the probabilities. For example, if this is the case, then how are we going to use it? So let's continue. So we use this parameter or this property of the data, entropy. So entropy will guide us on how to build, on how to choose our nodes in the decision tree. So what is entropy in the mechanical engineering sense? Very silent. Lignazzo.
I don't have an idea, sir.
We are mechanical engineering. You know, this is the first time you heard entropy?
It's there in thermodynamics.
Yes, exactly. What is it?
It's sort of a measure of order or disorder.
Okay.
I don't completely remember.
Okay.
But in a fluid.
Okay. Yes, correct. What else?
That's all I remember.
Okay. Who else have any idea about entropy? Chase Mukumane. Who is Chase? I mean, this is a new name.
Haone.
Haone. Okay. Any idea? Haone?
I googled it. May I read the definition?
Yes.
It's a thermodynamic quantity representing the availability of a system's thermal energy for conversion into mechanical work, often interpreted as the degree of disorder or randomness in the system.
Yes, exactly. It is the degree of disorderliness. The higher the entropy, the higher the degree, the higher disorder things are. The degree of disorderliness. The world is always going towards higher entropy. Okay? It's always going towards higher disorderliness. Okay? That's what we learned from thermodynamics about entropy, isn't it? Entropy is always greater than zero. Do you know this? No? Okay. Anyway, we can discuss that one next meeting, as well as my assignment of NP complete problem. Okay. Okay. For now, let's leave it, and then we can somehow get a more in-depth discussion on it. Okay. Anyway, for now, we say that we are looking at entropy as the degree of disorderliness, okay, of uncertainty. Okay. So the higher the entropy, the higher is the uncertainty. Here, more uncertainty, there is more entropy. Okay. So now, for example, this is the probability of the heads of a coin flip experiment. So your probability of having a heads is 0. Okay. When this is the tail, probability of having a heads is 1, where this is the head. Probability of getting the head or a tail is half. Okay, in this sense. Okay? So now, so here, this is where your tail is, and this is your head is. And then the entropy of, what is the entropy? The measure of entropy, which is this equation here. Okay? We're just writing this entropy equation here. Increases when your probability of getting head or tail is half. Okay? That means there is the least certainty of getting a head or a tail. Okay? It's very uncertain whether you get a head or a tail. The entropy is highest. In this case here, the probability, the certainty of getting a tail, okay, is high. Okay? It's 1. Okay? But this is probability of getting a head. You won't get a head here because this is tail. So probability is 0. It's certain that you won't get a tail here. I mean, you won't get a head. Okay? That's why the entropy is 0. Because it is certain that we'll always get a tail. Just like here in this case, probability of the head is 1 because this is the case where you get the head. Okay? So there's a certainty, it's very certain that you will get a head. And very certain that you won't get a tail. 0 certainty of getting a tail, 0 probability of getting a tail, 1 probability of 1 of getting a head. 0 probability of getting a head, and 1 probability of 1 for getting a tail. Okay. In the middle, we don't know. So the highest uncertainty is in the middle. Okay. So now, how do we compute this? Okay, let's compute. What is your y, I, and what is your yi? What is your output? Y is the output, y. And then, okay, let's just go here so that we can, okay, this is what we discussed already. Okay, here. So now this is the entropy plot that we discussed in the previous slide, and this is the table. So now you have the coin flip table, head and tail. So we only cut up to here. So in this case, this is the data that's given to us. So let's see that your output Y being true, excuse me, your output Y being true and Y being false. So the probability of Y being true, or the output being true, and the probability of the output being false. So in this case here, what is the probability of being true? So how many outputs, how many data sets that we have? 1, 2 data points. 1, 2, 3, 4, 5, 6. You have 6 data points, and the probability of it being true, the output is true, is 5/6, and false is 1/6. I think this is straightforward. Okay. So now to compute the entropy, we just plug into here, to this equation. So you have Yi, this is the output. Y, the big, okay. The big Y is your output, consisting of small y, Y1 and Y2. Okay. Where your Y1 is the true and the Y2 is the false. Okay. So in this case here, your I goes from 1 to 2 because there are 2 outputs of the Y. Okay. So this one goes from 1 to 2. So in that case, if you write it out, that means that H of Y, big Y, is equal to, there's a negative sign, negative of B of the big Y, that is equal to Y1 log 2. Log 2 is just a log function to the base 2. Probability of big Y equal to Y1. Okay. And then sum plus the negative of probability of big Y equal to Y2 log 2. Then probability of Y equal to Y2. Okay, then we just substitute. Okay, so here this is probability of Y equal to Y2. That's, sorry, equal to Y1, and this is equal to Y2. Okay, so substitute. So this is 5/6, and this is 5/6, and this is 1/6, and that's 1/6. So the result is here, and then you compute your entropy H of the big Y is that. So is that entropy big or small? What are the expected values of the entropy? What are the expected values? So log 2. Log 2 in this case will always be 1. Because it is based on probability.
It
so
should be less than 1.
Should be less than 1. Why?
Because probability ranges from 0 to 1.
And then?
And
it's a summation of all the other probabilities. So you take the probability, the first part of the probability, which is the true probability, that's a function of the true probability, and the other one is a function of the false probability, and you add them together. should always be 1, between 1 or 0. Okay, most likely. But then, so that means if we say should be always 1, between 1 and 0. So here, this is 0.65, so it's higher. It's bigger than 0.5. So that means the number is a little bit high. So this is a high entropy. Okay, in this case, this data that's given to us, okay, will give you a high entropy output. Okay, so that what does it mean? It means that there's a lot of uncertainty on what will be the possible output. Okay, you don't know. It's not deterministic, whether it's always be true or whether it's always be false. Okay. Anyway, let's continue. So it's just some ideas that we need to understand as we move along. So now there is that entropy and there is this conditional entropy. So in our case of the decision trees, it is not enough to consider the absolute entropy. You also need to consider the conditional entropy. So conditional entropy is the value of H, which is the entropy of the Y output given the X input. Okay, so in this case here, well, we just follow this equation. Okay, if you see this, what's the difference from the previous equation? In the previous equation, we only have probability of a certain output, okay, of the certain output Y, and then we sum everything up. But in this case here, probability of that certain output, before we sum it up, we have another summation inside of it, which is that particular, the probability of that particular input. Now it is before we sum up this, okay, sorry. Here, this is probability of the output, okay? Here, this is probability, absolute probability now applies to the input. Here, the output is now dependent on that input, okay? So now, the summation of the probabilities here of the output is now with respect to the condition or the given condition of the input, okay? This summation that was previously here is now taken with respect to the input. And now after the summation, you multiply it to all the possible inputs. Okay. So how will we compute it now? So in this case, for example, if you will look at X1. So look at X1 alone. Look at the output of this, just purely the output of the data set. Okay. So the output is 4. There are 4 that are true. Hello. Okay, given X1 that is true, in this case, X1 that's true, everything is true. And then there are 0 false for X1 that is false. There's 1 true and there's 1 false. So now, if your probability of X1 being true, it is how many? This is 4 out of 6. And then probability of X1 being false is true out of 6. So these are absolute probabilities. Now we will consider the output of Y given X1. So how is this computed? So in this case here, this is, I should write it down. I didn't write it down here. So let's consider this. Okay. So let's write out this one. Maybe I should write out. Or here, so that it's bigger. So what we're applying here is just applying the conditional entropy so that we can use it later in terms of building our decision tree, to decide which node will come in first. Okay. So now, if that is our entropy equation, the relative conditional entropy equation So this part, when your K is equal to 1, so you have P of Y output true given X input that is equal to X1. Okay. Log 2 of P of Y that is true given X that is X1. Okay, plus, because this is summation, it goes to K1, director inputs. Y equals false given X equals X1 log 2 P of Y equals false given X equals X1. Okay, then multiplied by this one, negative multiplied by negative of probability of X, big X, equal to X1. Okay, and then because that's a summation, so this one multiplied by that. Okay, maybe this one will, I should remove this. Okay, then we add with another term plus, plus the negative of P now of, we are looking at this one only, sorry. So we are looking at this part here, H of Y given X1. So H of Y given H1 is this. I'm computing everything here. Okay, this is H of Y, big Y given X1. What does it mean? Because it is given big Y, that means all the possibilities of Y. So now is this the one? So you have Y being true, okay, given X1, okay, plus Y being false given X1. Is that all the possibility, all the forms of the Y output, true or false? Yes. So that means that the entropy of all the values of Y given X1 is computed using this equation. So let's check. So what is no, sorry. We have to include this part here where your X1, because this is conditional probability, we have to include X1 before this one. Okay, let's just consider first this part. Okay, this part is this part here before we add this part is this part. Okay, this one is, okay, let's go here. So Y given true when X1 given X1, Y is true. So this is X1, okay, given X1 and Y is true. So that is 4. So that is 4 with all the the output is 4 over 4. So that is 1. Okay. And then, is that correct? So given x1, okay. If it's not clear to me, it should not be clear to you. So let's start from the start. So we have to consider what is this probability. What is this term? What does it mean? Probability of the y being true given x1. So now this is x1. Okay. Is that correct? So your x goes from, your x is that true? Okay. Somehow I get lost in this. So your y, so you're given x1. So your x1 has a value of true or false. Okay. So now your output can be true. Okay. The total output here in terms of the y. Okay. In terms of the y, this is your y. Okay. So now, what is the value? When is y is, well, what is the probability that y is true given x1? So now, okay, y is true. So y is true given x1, given x1 being true or x1 being false. Okay, so here, for example, here we have in this case here, the output is 4. The output is true. So x1, so I think here x1 should be true. Let me check. Okay, yes. So in this case here, x1 can be true or false. So here, because x1, okay, that is the confusion there. Let me write it out in another way. Okay, there is a confusion there. In this case here, your x1 goes through your x, that is x1 here. This is the confusion. I should change this one. So your small x1 here, this is the property of x1, and that x1 is and that xj is x1 and x2. There is that confusion. Okay, let's do it here. So this is the case of your xj, where your j goes from 1 to 2, which is your, I should rewrite it, x1 and x2, sorry, x1 and x2 input. That is okay. That is your x1 and x2. Here, in your, when you're talking about your x1 here, I mean, in this case, your x1 can okay. Anyway, so I should redo this indexing because it makes a lot of confusion. Okay. Okay, let me redo. Let me start from here. So this big X, okay, there's only 4 minutes. Let me just make it clear, because even from it won't be clear for you if it's not clear for me. The big X there, okay, in this case, this big X, okay, is X1, okay? And your X1 can become true and also false. Okay, so here, this is X1. That big X is X1. Okay, can be true or false. This is true or false. Okay, so here, this is true or false. That is the output given a true or false of X1. Okay, there is no X2 here. This should be H, that's the confusion there, H of X of Y of X1. That is exactly what it is here, X1. That's a confusion. There's no X, this should be X1 here. So here, that is why there is that X1. Okay, so that means that in this case, we only consider X1. Given X1, so given X1, that one can become true or false. So H of Y given X1, big X1, is equal to here. This is minus of P. Okay, let me rewrite this. Minus of P when X1, big X1, is equal to true. Okay, and then now the summation inside this part. Okay, probability of the Y being true when big X1, okay, when big X1 is equal to true. Okay, log of 2 probability. Okay, don't think about X2 first. Y being true and probability of given condition of X1 equal to true. That's summation. Okay, and then plus, okay, this part, the negative of P. Again, this is X1 equal to false now. Okay, so, and then the summation of probability of, let me just finish it because it's not, now this is false. Okay. Probability of being true. There's a missing part. This is not complete. That part. This part here, this is summation plus probability.
Patala,
Yeah, I say, guys.
Hey,